Hey guys, today we're looking at 6.4, which is going to talk about definite integrals. So the notation for a definite integral, we're going to use our integral sign, and it's going to go from A to B, which are going to be numbers, and then you're going to have some function, f of x dx, right there. So we've talked about Riemann sums, and we've talked about how they can approximate the area under a curve, and we've talked about how an integral is the exact area under a curve. So our definition that we are going to use here, so an integral, let's make that text a little smaller, is the exact area, and let's say between a curve, say f of x, so whatever that function is, and the x-axis on the interval a to b, which you'll notice are the same letters that we have in our notation for a definite integral. So our integral is the exact area. So now we're going to start talking about some exact areas. And so let's look at this graph that we have right here. And we're going to find some specific integrals. So the first one it wants us to find is from 0 to 4. So we're trying to figure out from 0 to 4, which is this semicircle that we've got right here. Our semicircle right here is from 0 to 4. So if we're trying to find that exact area, well, we know how to find the area of a circle, and a semicircle is just half. So we take the area of our circle and divide it in half. So our area for a circle is pi r squared. So we're going to look at pi r squared divided by 2. And our radius is going to be 2 units. So I'm looking at pi times 2 squared divided by 2, or 4 pi divided by 2, which would just give us 2 pi. So our first area there is just 2 pi. It's that area of that semicircle. The next one we're going to look at is from 4 to 8. So from 4 to 8, that's this trapezoid right here. So to find the area of a trapezoid, we have the 1/2 base 1 plus base 2 times our height. So we're going to have 1/2 times, well, our base 1 is 1, 2, 3, 4 units, plus our base 2, which is like the top right here, which is just 1 unit, times our height, which is 2 units. So that 1/2 and 2 cancel out, so we're looking at 4 plus 1, which gives me 5. So the area for that trapezoid is 5. And then we are going to look at from 8 to 12. So from 8 to 12 is this triangle right here. So to find the area of a triangle, we just do 1/2 times the base times the height. You'll notice that all of our other ones were above the x-axis, and this one is below the x-axis. So for this one, it's actually going to be negative because it's below, it's in that bottom half of our graph. So I'm going to have a negative 1/2 times my base, which is 1, 2, 3, 4, times my height, which is 2. The 1/2 and 2 cancel out, so it's just a negative 4. Okay, the next one that we are looking at goes from 0 to 8. So from 0 all the way over here to 8 is going to be the semicircle and the trapezoid. So I'm just going to take those and add them together. So it's just going to be the 2 pi area for the semicircle and the 5 area for the trapezoid. So 2 pi plus 5. I can't simplify that anymore. And then our next one over here, it's from 0 to 12. So going from 0 over here all the way over to 12. That's all 3 of our shapes. So I'm going to have the 2 pi from the semicircle. I'm going to add the 5 from the trapezoid, and then I'm going to subtract the 4 from the triangle because it's below So 2 pi plus 5 minus 4 gives me 2 pi plus 1. So my area for the whole thing is 2 pi plus 1. All right, let's look at another example. So this one is talking about the velocity of a particle moving along the x-axis graphed with the line segments and semicircles below. So it says find the integral from 0 to 10 of our velocity. So that means that we are going to find all of these areas here. So I'm going to break it down into some smaller sections that are going to be a little bit easier for us. So I'm going to break it down right here. I'm going to have my first shape, which is going to be a trapezoid kind of looking shape. Let's draw that line a little bit better. Then my second shape is also going to be a trapezoid right here. My next shape is just this semicircle. So I'm going to keep that semicircle how it is. And then my last shape over here, I'm going to make this little triangle. So there are my 4 shapes there. I've got the trapezoid over here. I've got my trapezoid right here. I've got my semicircle. And then my triangle. All right, so if I'm trying to find the area for this trapezoid, I'm going to have 1/2 times my base, which is 1, 2, 3, plus my other base, which is just 1, times the height, which is 2. The 1/2 and the 2 cancel out, so I have 3 plus 1, which is 4. Then for my next trapezoid, I'm going to have the base, which is 1, 2, 3, so 1/2 times 3 plus my other base, which is 2, times my height, which is just 1. So this time they don't cancel out. I'm going to have 1/2 times 3 plus 2 is 5. So this is going to give me 5/2. Next, I'm going to look at my semicircle, which is going to be my pi times my radius, which is 2 squared divided by 2. So 2 squared is 4 over 2 is just 2. So that's just going to give me a 2 pi for that semicircle. And then I've got my triangle right here, which would be 1/2 times my base times my height. Both of those are 1, so it's just going to be 1/2. So if I'm trying to find that whole integral, I'm going to add all these together. But remember, if they're below the x-axis, they're negative, and if they're above the x-axis, they're going to be positive. So when I'm finding my integral from 0 to 10, I'm going to have a -4, or sorry, let me put that v of t dt. It's going to equal a -4, -5/2, a positive 2 pi, and a positive 1/2. So if I do a -5/2 and a positive 1/2, that gives me a -4 over 2, which is just 2, and then a -4 as well. So a -2 and a -4 give me a -6, so I'm going to have 2 pi minus 6. And then when it says, what does it represent? Well, we've kind of talked about it, our relationship between our position, our velocity, and acceleration. So if this whole graph is the velocity, the integral goes backwards to the position. So it's going to represent the position of the particle, or we could also say the particle's displacement. Okay, so if we are talking about part B, what is the total distance traveled? So when we're talking about total distance, it's a little bit different than displacement. Our total distance, we're going to make all of these positives. Because basically what's happening is here it's moving to the left and here it's moving to the right. So we need to figure out the total distance traveled. We're going to make them all positive. So that means that I'm going to do my 4 as a positive plus 5/2 plus 2 pi plus 1/2. So 5/2 and 1/2 is 6/2, which is just 3, plus 4 gives me a 7. So it's going to be 2 pi plus 7 is the total distance traveled. All right, part C is going to ask, when is the particle speeding up? So remember, it's speeding up if our velocity and acceleration have the same sign, and it's slowing down if velocity and acceleration have opposite signs. So if I have my position, velocity, acceleration, let's do our little sign chart here. I'm looking for where my velocity and acceleration are both positive or both negative. So I'm looking for where my velocity is positive, and if the acceleration is positive, that means my velocity is increasing. So where it's positive and increasing starts here at 5 and goes to that 7 right there. So it's this little part of the semicircle. Down here it's negative, so we're not even going to look at that part. Here it's decreasing, so then our next part is going to be the little triangle right there. So I'm going to say that it is speeding up from 5 to 7, and then also from 9 to 10. And I'm going to say because the velocity and acceleration have the same sign. Then I also want to figure out where is it slowing down. So it's going to be slowing down where they have opposite signs. So if it's negative here, it's going to be slowing down where it's increasing. So that's going to be from 0 up here to 2. Then it's not increasing there, but then it's also increasing from 4 to 5. And then it's also going to be where my velocity is positive, but my acceleration is negative, so the velocity is decreasing. So it's also going to be this other part of the semicircle right here. So we've got those 3 pink intervals. So it's going to be from 0 to 2, then from 4 to 5, and then from 7 to 9. And it would be because they have opposite signs. All right, part E says, how much does a particle move to the left? So remember, it's moving to the left when our area is below the x-axis here. So it's moving to the left with our 2 trapezoids. So I'm going to add those together. It's going to be a 4 plus 5/2. Well, if we wanted to rewrite 4 as a fraction, I could do 8 over 2 plus 5 over 2, which is going to give me 13 over 2. So it's moving to the left for 13 over 2 units. Actually, our units are, right here it says centimeters per second, so that can be centimeters, that should be centimeters, and that should be centimeters. And then the last one asks, what's happening at t equals 7? So at t equals 7, that's this point right here. So at t equals 7, our velocity has a maximum. So I'm going to say that the velocity has a max. So what that means is that our acceleration is equal to 0, because that would be our tangent line right there. And if we're going the other way around, wherever our velocity has a maximum, so between a min and a max, that's where it changes from increasing to decreasing. So our position, that would be where it changes from concave up to concave down, or the other way around. So our position would have a point of inflection. So I'm going to say that my position is x of t, and it's going to have a point of inflection. All right, so that one was a lot of different parts. Let's look at our next example. Or actually, we're not going to look at examples. We're going to look at some properties of definite integrals first. So Some properties, some rules that you're going to need to remember, the zero integral. So that means that if I have an integral that's going from one point to the same point of my function, that is going to be 0 because it's just a point. There is no area between the curve or anything because it's just at one specific point. Next is negation. So if I have the integral from a to b of f of x dx, that's equal to negative integral from b to a of f of x dx. So if you switch the a and b, you got to put a negative in front. Our next one says multiply by a constant. So if I have the integral from a to b of k f of x dx, I can take the constant out and then take my integral. The next one is decomposition. So we're assuming that a is less than b, which is less than c. So I'd have the integral from a to c of f of x dx. Well, that's equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So if I'm going from one endpoint to the other, I can split that integral. I can decompose it into two different parts, or even more than two parts if needed, which we kind of already talked about that with all of our different shapes that we were adding together in the other examples. And then the last one are addition and subtraction. So if I have the integral from a to b of f of x plus or minus g of x dx, I can split that. So I have the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So that can be split there. So those are some properties. Let's look at some applications of those properties. So it gives us some definite integrals. We don't know what our functions are, but it gives us these definite integrals. Let's look at what we can find. So this one, part A, says the integral from 5 to 1 of f of x. Well, the integral from 1 to 5 is -3. So if we have this where we switch them, that's going to be putting a negative in front of our 1 to 5 integral. So if that was a -3, it would be a negative -3, which just gives us 3. All right, the next one is from -2 to 5 of f of x dx. So that's going to be our decomposition. That can be the integral from -2 to 1 of f of x dx plus the integral from 1 to 5 of f of x dx. So I would take my 4 and add the -3, or 4 minus 3, which just gives me 1. All right, looking at C right here, we're actually going to use two of our rules. We've got an f of x and a g of x, so I'm going to go ahead and split those using our addition subtraction rule. So I'm going to have the integral from -2 to 1 of f of x dx plus our integral from -2 to 1 of 2g of x dx. And then that 2 is going to be my constant rule. I can take that out. So it's going to equal the integral from -2 to 1 of f of x dx plus 2 times the integral of -2 to 1 of g of x dx. Well, -2 to 1 for my f of x is 4 plus 2 times our g of x1 over here is 8. So 4 plus our 16 is going to give us 20. All right, D, we're going from 0 to 1 of f of x dx right here. So if I'm looking at these three integrals, there is no 0 on any of my bounds here. I've got a -2 to 1 and then 1 to 5. So I need to somehow split this one, but I don't know how I can split that. So with the information that we are given, this one is not possible to find. So I'm going to say not possible with the given information. All right, looking at E right here, we're going from 1 to -2 of f of x, and we've got a 3 there. So I'm going to pull that 3 out, and then I also need to flip these. So there's going to be a -3, the integral from -2 to 1 of f of x dx. So the 3 came outside, and because I flipped these, I put a negative in front. So that means I'm looking at -3 times r4 for that integral, which is from up here. And -3 times 4 is going to give me my answer of 12. And then our last one right here, we're doing an integral from 5 to 5. That's the same endpoints, so that's going to be our 0 integral from 0 to 0. All right. Now we are going to look at some graphs, and we are going to set up the integrals. So we're going to get some practice writing our integrals. So we've got our f of x right here, and we want to go from -3 right here to a +3 right here. So that's going to be this area right here, and then this area right here that we're trying to find. So if I'm going from -3 to 3, those are going to be my bounds. So I'm going to go from -3 to 3 right there. And then I'm going to put my f of x equation. So I'm going to have it as 1 over 9x cubed, and then I have to put a dx on the end. So that's how you would practice writing your integrals. Let's do this one over here. We want to go from -1 over to 1, 2, 3, 4. So that's going to be that part, and then also this part right here. So I'm going to have my integral from -1 to 4, and then I'm going to put in my y, which is 3/4 x squared minus 2x minus 1, and then a dx on the end because that x is our variable. So that's how you would write your integrals if you're given a function and some bounds, so some intervals that you're looking at there. That's how you would write your integral. And so the last thing that we're going to do for these, we are going to sketch our graphs, and then we are going to use our calculator to find our definite integrals here. So if I'm looking at 4 minus x squared, well, that means I'm going to have a parabola that's been shifted up 4 units, and then the minus means that it's opening down. So it's going to give me this graph right here. And then I'm looking between -2 and 1, so from this point to this point right here. So this is the area that I'm looking at. And it's not a nice shape that we know how to find the area of. It's not a circle or a trapezoid or a rectangle or a triangle or anything like that. So we're going to use our calculator to help us find this integral. So give me a second while my calculator app opens on my computer. So what I'm going to do is I'm going to hit math, and then I'm going to scroll down to this option 9 right here, the FNIT, a finite integral. Oh, too far. Finite integral. So the example that we're looking at over here, it's going from -2 up to 1, and my function is 4 minus x squared, and then I'm going to put that x over here on the end for our dx. And I'm going to hit enter, and it pops out the area for me. So this one equals 9. All right, my next one right here, I'm looking at the square root of x minus 1. So that minus 1 means that it's been shifted to the right one, and it's the square root graph right here. And we're looking at our area from 2 to 3. So we're looking at this little section right here. So let's plug it into our calculator. So I'm going to do math, and then you also could hit the number 9 instead of scrolling down to 9. And we're going from 2 up to 3, and my function is the square root of x minus 1. So there is my function. I need to scroll over here and put an x after that d for dx, the derivative with respect to x. Integrals, remember, are antiderivatives. They undo a derivative, so that's kind of why we have that dx there. And then I'm going to hit enter, and it gives me this decimal. I'm going to round it, so I'm going to have 1.21895. So it's equal to 1.21895. So sometimes it's not nice, pretty numbers, and that's okay. All right, and then this one right here, I have x over 3 minus 1. Well, that's just a line, with my intercept being a -1 right here, and my slope being up 1 over 3. So that's going to give me a line. Ooh. And we're going from -2 to 4. So I'm going from this -2, 1, 2, 3, 4. So it's going to be all of this area right here and then a little area right there. So let's plug it into our calculator. We could do this one by hand. We could take our triangles and figure that one out. But we can also use our calculator. So let's do math. 9. We're going from -2 up to 4. And I'm going to hit alpha y equals enter to get my fraction x over 3 and then -1, put the dx on the end, and we get a -4. So our area there is -4. And like I said, we could have done our triangles, but you'll also notice that this right here is not a pretty point for our height. So we would end up with a 1/2 times, what is it, 1, 2, 3, 4, 5 for our base, and then our height would be probably like 1 2/3, which would not be a pretty height. It would be some ugly decimal. So that's why we would want to use our calculator for this one. That would be a little bit easier to figure out. All right, that is it for this set of notes. You do have a Go Formative homework that goes with this, so please make sure that you work on that Go Formative. Have it done by the time we come to class again, and you guys have a good day.